Very warm welcome to all of you to tonight, Building Bridges. So we began, I think the aim of us little group getting together was to really trigger reflection in exploratory thoughts towards the betterment of our world, towards greater flourishing, if you like, and importantly, to reach out to others, to all of us, not in the sort of, just to, glean greater understanding through the sharing of ideas, not in the sort of polemic way that we're used to in the world at the moment, with extremes of views. One is right and one is wrong. And this doesn't seem to lead to flourishing. Whereas when we open ourselves up to everybody's views, we can move forward in a more positive way. Okay, so why now? Well, it was the pandemic that threw up a lot of questions, a lot of issues like climate change, like disease. It's no respecter of boundaries. A virus, as we know, doesn't have a frontier. So our ethos in Building Bridges is that the Earth, in all its beautiful diversity of people and geography, from one angle and in one big sense, we can look at it as one country. Many of you may have seen that image of the little blue spot in space of Carl Sagan, this beautiful planet that we inhabit. So we all of us, regardless of race, religion or no religion, we're citizens of this country, and we each play a part, however big or small, in helping it to flourish. And sometimes we liken the world to a human body. If you get a pain, if you have a migraine in any part of your body, it affects the whole body. When you have a migraine, you take your body to bed, not just one part of it. And in this way, something that happens in one part of the world affects all of us on so many levels, whether that's disease, economics, climate change, or whatever. You don't need to be an expert. Some people are experts. It's more about caring for the planet, being concerned, and helping within our localities towards the pressing and urgent needs of our time, the times in which we are living, and to share in the joys that are apparent in the world too. So now I'll hand over to Phil Kumen, who's going to introduce Dr. Warren Houghton, who's our speaker for this evening.
So I'd like to describe Warren as a communicator. He makes science accessible and understandable to people like me who think they don't understand science. I remember a conversation with him about 20 years ago when he explained to me that the idea that the universe is random, that belief so many people hold, is actually in fact unprovable. At least that's what I think he said, but he may correct me now. Career-wise, he's had 40 years in education at all levels. So he's taught postgraduates and he's also taught 7-year-olds. He's got 3 degrees and a PhD, including a PhD in physics and electronic engineering. The theme tonight is Science True. I always enjoy listening to Warren, and I feel he's removing a few of my veils that obscure my understanding of science. I think we are in for a treat this evening, honestly. The topic, as I mentioned, is science true? Sounds like a binary question, but in Warren's hands, I think we'll be in for a few surprises.
Okay, thank you. I will start screen sharing, if I may. I've got some PowerPoint slides just to put up questions and hopefully not baffle you too much. So in a sense, what is science true is sort of the short version of in what sense can scientific theories be described as true. I'm attacking this because the perception that's often presented, particularly when we get down to issues between science and religion, is that religion's all wishy-washy faith and science is proved to be absolutely true. And yes, it's not quite as simple as that. It's much more nuanced, I think. But I'd like to start just by, as a Baha'i just going back to what a couple of things we find in the Baha'i writings about science and religion. If I can get so just a few quotes from Abdul Baha, the son of Baha'u'llah, the founder of the Baha'i faith, and then from Shoghi Effendi, his grandson. If I read one, Jeff, will you read the second one for me, just to give people a break from my voice? So if I read the first. So one of the quotes that people use most often in the Baha'i faith, because the Baha'i faith has one of these principles that science and religion should be in harmony. So, and I think that takes quite a bit of explaining, particularly in a world that thinks, or so many people, not everybody, so many people think that that's completely the opposite from reality. So Abdul Baha, this is the most commonly quoted quote: "Religion and science are the two wings upon which man's intelligence can soar into the heights, with which the human soul can progress. It is not possible to fly with one wing alone. Should a man try to fly with the wing of religion alone, he would quickly fall into the quagmire of superstition. Whilst on the other hand, with the wing of science alone, he would also make no progress, but fall into the despairing slough of materialism."
Put all your beliefs into harmony with science. There can be no opposition, for truth is one. When religion, shorn of its superstitions, traditions, and unintelligent dogmas, shows its conformity with science, then there will be a great unifying, cleansing force in the world, which will sweep before it all wars, disagreements, discords, and struggles. And then will mankind be united in the power of the love of God. Abdul Baha, Paris Talks.
So Abdul Baha, whose writings are very influential to all Baha'is, makes it really clear that as Baha'is, we've got to take science seriously. And the last quote I've just highlighted in red, one particularly relevant bit. The highlighting in red is mine, obviously. This was Shoghi Effendi in a letter he wrote in 1934. "The revelation proclaimed by Baha'u'llah, his followers believe, is divine in origin, all-embracing in scope, broad in its outlook, scientific in its method, humanitarian in its principles, and dynamic in the influence it exerts on the hearts and minds of men." So for a religion to claim to be scientific in its method is something I think a lot of people outside my faith would find a bit unusual, to say the least, I guess. But I think it means we need to try to explore what scientific in its method might actually mean. So that's really what I want to try to explore a bit this evening. Because I think people can oversimplify scientific, the idea of science. I think this isn't everybody, but I think some people think science works like this. So the picture that I think some people have is scientists make observations of the real world, they accumulate a whole load of facts, and then they go from there to proof of a scientific theory. Well, what I want to suggest is it's not quite that simple. Let's first take the idea of proof. What do we mean by proof? Well, if you're in a court of law, you're talking about beyond reasonable doubt, or civil court on the balance of probability. I don't think that's what people think we're talking about. I think a lot of people assume we're talking about deduction, as in what people might remember from doing geometry theorems in maths at school. The syllogistic logic, going back to Aristotle, if A is true and B is true, then C is true, type of deductive logic. Actually, scientific theories are not proven that way. If we go back to the early part of the 20th century, when the dominant scientific philosophy was logical positivism becoming logical empiricism. It was a very broad school. The talk was largely about using induction. I've seen lots of swans. All the swans I've seen so far are white, therefore swans must be white. And induction has a problem. The classic quote of Bertrand Russell, used to use it quite often, was imagine a load of turkeys wandering around their yard, pecking away, and every morning the farmer appears and feeds them at 8 o'clock. And so they form the inductive theory that whenever the farmer appears, they're going to get fed. And then Christmas Eve arrives. So induction has a problem, doesn't work perfectly. And if you go back to the Scottish philosopher David Hume, he put it forward as a massive problem for science and lots of philosophy generally, in that, as he put it, just because we've seen the sun come up every day doesn't mean it's going to come up tomorrow. We cannot prove that what we've seen happen regularly so far will continue to happen. So from a term of proof, induction is useful, but it's not perfect. And what scientists really use is better described as abduction, or inference to the best possible explanation. And even that is problematic, because if you say inference to the best explanation, it's best of what? You know, you've looked at a load of accumulated data and you've come up with an explanation, or you've come up with a few explanations and you're trying to pick the best one. But the best one might not be correct. It might be the best out of a bad lot. So that has problems. And there's even a big problem of defining, what do you mean by best? Does it mean explanation that fits the observations very accurately? Or is it a good fit with current scientific theory? Scientists don't like to throw out the previous theory in too much of a hurry. Or is it elegant with nice mathematical equations which look beautiful, which is an idea which physicists find quite understandable? I know Philomena's mentioned this a couple of times. Einstein used to say the mathematical equations should be beautiful. We could think of background. Or is the theory something that will stimulate more research, or does it offer solutions, or does it come up with values which are obnoxious? So best is not actually that simple. So from evidence, trying to get a theory is not as straightforward as it was once thought. So if I move on. So what I want to think about is now, how do we arrive at a scientific law? This idea of deduction, perhaps stay with that for a bit. Sort of one of the most well-known bits of law is Newton's laws, his 3 laws of motion and his law of gravity. And how were they proved? Well, they're not proven. Newton's laws and his law of gravity are not proven. Deduction is used. So what Newton did, Isaac Newton, after the work of Tycho Brahe and Kepler to provide a model of the motion of planets, Newton was able to take his 3 laws of motion, his law of gravity, and there he did use deduction. That was where he, in parallel to Leibniz, invented calculus to do it. He showed that starting from his laws, he could arrive at predicting the observed planetary motion. So, and there's a very key phrase down there which isn't mentioned enough: within experimental uncertainty. There's always experimental uncertainty in any measurements. But his laws made predictions which fitted the observations. So that provided very good evidence but it's not proof. There could be other explanations. And it turned out round about 1900-ish, when Einstein and other people started probing a bit deeper, Newton's laws turn out not to be quite right, not in extreme circumstances. So there's a really important lesson for all scientific laws there. Apart from them not being absolutely proven, we then discover they're not permanent, they're provisional. So scientific laws are always provisional. They're valid until we get more evidence and they get overturned. So, and then there's a question, what do we mean by a scientific law anyway? I go to that. So what is a law? If we take Newton's laws of gravitation again, still to stick with that, he couldn't explain why his law of gravity worked. He postulated that two large masses experienced a force of attraction. He could offer no hypothesis as to why there was an attraction. So his law of gravity wasn't explained. In fact, that was one of the big arguments at the time. He had a lot of arguments with Leibniz and other people because they didn't like there being no explanation, this action is a distance. But it's not an explanation, it was a description. And this is where we get into different views of science, because one approach to science is to look at what we might describe as a law. It's not the same as a law in society. A legal law is something you're supposed to do. What we're looking at in science is really just trying to give a description of what we observe to happen. And if we can put an equation to it to predict what that looks like, that's quite helpful. So it's not an explanation, it's a description. There is a different view because a lot of mathematicians, and this is where we're going back through Plato to Pythagoras, I've noticed that maths, quite often mathematicians have come up with all sorts of new mathematics that many, many years later, sometimes centuries later, have proved very useful in describing the real world, which leads people to talking of God as the great mathematician and that sort of idea. So there are different views on this, but quite a few people see laws as just descriptions of what happens. So trying to get to a slightly more nuanced description of how science works. This is a bit more complicated, so I'll take a bit of time to try to explain this. So the real world, if we think about our observations, there's a great story of Karl Popper, a philosopher of the around about the middle of the last century, who used to, in some of his lectures, tell his students, right, for the next 10 minutes, I want you to write down your observations. And they'd all look at him, yes, observations of what? What are we supposed to be? And that's the problem. You don't just observe the world, you observe what you look for. So before you start observing stuff, you actually have some idea as what you're looking for. And you have an idea as to what is relevant, which depends on your existing theory. So your observations are not just completely value-free, completely clean observations. To give an example, suppose when I was teaching at school, and maybe a student would come into me in my electronics lab and he would say, I've got a problem with this circuit. I've just measured a voltage in this bit of the circuit as being 4.23 volts. Well, my question then is, what is the fact? Is the fact that the voltage is 4.23 volts? Well, has he measured it correctly? Does he know that it's an alternating current? Has he used the right scale on the voltmeter? There's all sorts of questions. There's also the we've used this complicated thing of voltmeter, so there's a whole load of theory behind the measurement in the first place. So the measurement wasn't just a clean measurement, it was dependent on existing theory. The only fact I have, as far as I'm concerned, is the student has told me he measured 4.23 volts. The fact isn't that it was 4.23 volts, the fact is he said it was. So that's why we use the phrase observation statement. So what we have to base our scientific theories on are statements of what people say they have measured. And those are highly dependent on your existing theory. We know, for example, that our senses, if we're relying on our senses, they can be fooled. Just in what we see in the world is influenced enormously by the assumptions we're already making in our unconsciously. And if we're starting to do any more complicated science, we're using complicated instruments, which we have designed to look for certain things and not other things. If you use a telescope to look out into the night sky and you use an optical telescope, you're not going to see anything in the infrared. If you build a Large Hadron Collider to smash atoms together, you've already got a very specific idea of what you're looking for. So you've got a lot of assumptions behind what you're doing. You've got definitions of what you think is a good theory. You've got existing theory affecting how you take your measurements. And so the whole process of arriving at a scientific theory is rather more complicated. So you go through this abduction, this inference to best possible explanation, form a hypothesis, you keep testing and trying to falsify it, though you don't immediately throw out a theory but just because it looks wrong at the first, because there could be lots of other things that have been wrong in the experiments. And then you form a provisional theory, which you will often, as a scientist, commit to. You will act as if it's completely valid, but you should remember in the back of your head that it's only valid until more evidence comes along and has to be replaced. So it's not a simple case of just gathering facts and proving a theory. It's rather more complicated. Now, trying to get to this idea of truth. So if we think of science, we've done all these experiments, we've come up with an explanation, we've got a theory, or often we talk about a model. Now, in our model, we might often postulate things that we can't see normally. So, like, for example, back in the 19th century, people were doing a lot of work on gases. And they were postulating little molecules of gas randomly zooming around at very high speeds. As far as a lot of scientists were concerned, those were fictional. They couldn't see them. So they would be described as unobservables. And some people were happy to accept them as being a useful idea. Some people, no. And in a sense, that leads to two extreme approaches to how you view a scientific theory. So if you take the idea you've got a scientific theory, you've got the theory, you've got the state of the world, this state, you know the state of the world, you use the theory and it makes predictions. Now, at one extreme, there are scientists who would be called anti-realists or even instrumentalists, who would say, I don't care about the internal workings of that model. If it makes the right predictions, that's all I care about. And the internal workings of that model are just a convenience. So you don't see them as being true. At the other end of the extreme are what we call scientific realists, who see those unobservable, the internal working of that model, as telling us something really true about the world. So this is where we've got this range of ideas from whether it's true or not. And so, in a sense of both being a physicist and an engineer, I can appreciate both sides of this. As an engineer, I might just be happy with a prediction. If I've got a theory that says if I build an aeroplane in this way, it will fly, I don't really need to worry about whether all the inner workings of that theory are correct. If I'm a physicist, I'd probably be a bit more concerned. Perhaps a really interesting side to this is, in a way, this is what got Galileo into trouble. When Galileo was supporting the Copernican model, he'd effectively been told by Pope Urban, who had been his friend, that he could teach the Copernican model as a technique for calculating positions of planets, etc., as long as he didn't claim that that's what was actually happening. So if he presented it in the anti-realist way, he'd have got away with it, but Galileo insisted that it was what was really happening, which of course we all agree with now. And that was what part of what got him into trouble. I always find a really good analogy for talking about this idea is to think about a map. So a map is a model. So if I think, last weekend I was out walking around Dartmoor, and I have a map. So is a map true? Well, reading the map as an experience is nothing like being stood out on Dartmoor. And it's not squelchy and wet when I put my foot on it. And the roads aren't red and yellow. So in one sense, of course, the map's not true. The only way to make a true map in the absolute sense is to make a complete perfect scale model, which is a bit pointless. Not scale model, full size model. But it does nevertheless tell me a lot of very true things. It's very, very useful. It enables me to get from A to B. It tells me that if I walk down the road and take the second turning right, I'll get where I want to go, etc. And you can also think in terms of, it's sort of like there's a difference you can see between using Newtonian mechanics and relativistic mechanics, in that, as an analogy, be careful not to take the analogy too far. If you just want to drive across Dartmoor, you might settle for a 1 to 50,000 map. If you want to go out walking on the moor, you might then want to go for the 1 to 25,000 map, the more detailed one, which is sort of, I think, is a bit of analogy to, if you want to do normal everyday mechanics, you use Newton's theories. If you're going to go near the speed of light or near some incredibly large masses, you're going to have to use Einstein's theories. But you still go back to Newton when you want to do the simpler stuff. So the other thing I perhaps ought to wrap up in a moment, but the other question I want to address is the idea that's often presented as scientists don't have faith. That's what religious people have. They only accept what they have seen evidence for. You may have heard that a few times. Well, as a scientist, I've gone into school and I've taught an awful lot of science that I have not seen the evidence for myself. No scientist has seen all the evidence. So this, we only accept what we've seen evidence for, actually isn't true. So we've got to ask, well, why do I accept it? And I accept what a lot of other scientists have said. I have a lot of trust in other scientists, or you might say faith in other scientists. I think it's a very reasonable valid faith, but it is, in a sense, I can't prove that what other scientists have told me is correct, because I haven't actually looked at the evidence for myself. I've trusted them. So, I have to ask, why do I trust other scientists? Well, having worked within science, within the academic world for a little while, I've seen what's involved. I've seen how scientists tend to question everything. I've done a little bit of that myself and shared ideas with other people. And so I've learned to trust other scientists. Not absolutely. I know other scientists get things wrong. So it's not with everything other scientists say is absolutely valid, correct. It's with a degree of caution that I read anything that I see written by the scientists. But in general, I have faith in that scientific community, which has been built up over time, experience, which I think is something which isn't a million miles away from the faith people might have within religion. And there's also, going back to this problem of induction, scientists have faith that the world is consistent, that induction will continue to work, that there are laws to be found. You can't prove that is the case about the world. You can't prove that science will continue to provide useful answers, but scientists carry on as if it will, which is I would argue, a form of faith. And I'd just like to finish with one last question, because I've been coming from the world of physics a lot. So I just want to think science nowadays is much more than physics and chemistry. It includes social sciences and psychology and economics, and has done for quite some time. And I would suggest that there is a difference between what people call the natural sciences and the human sciences, which has created within the scientific world quite a lot of controversies. So what's the difference between natural sciences and human sciences? The natural sciences, we're dealing with the inanimate, things that just sit there and do as they're told. With human sciences, we're definitely dealing with animate things, people, not things. With natural sciences, if you imagine you're doing something with, say, an electron, one electron is very much like another electron. Actually, in a very profound way, one electron is like another electron. And what it was doing yesterday doesn't really seem to matter. Its life history doesn't seem to matter. And what you do with an electron in a lab will work out in the real world, which is why we're able to talk to each other using Zoom at the moment, because everything that was done in a lab is fairly consistent out in the real world. So when we're dealing with the inanimate, what we do in the lab with very simple experiments work. The moment we go to humans, and there's a sort of fairly, not a hard boundary, I think somewhere in the world of biology is where the boundary rests. What you're no longer with what they were doing yesterday doesn't matter. Their life history matters. They're massively more complicated. And also, if you take, for example, economics, you come up with a theory. Well, if you come up with a theory about an electron, the electron doesn't read your paper about what you've just said. But if you come up with a theory in economics, you're going to get people reading the paper, and that's going to change their behavior. So the moment we get into human sciences, I think things change a lot. And I think natural sciences have developed over the last many hundreds of years, and there's been philosophy associated with natural sciences for a long time. And at the start of the 20th century, the philosophy of science, the world was in physics. More recently, philosophy of science has been more concerned with biology and very much more concerned with human sciences. I think things are changing. There's a lot more to be said about how science works once you get to dealing with the animate. I'm thinking I've probably thrown enough ideas out there for the moment. Is that a good place to stop and let people chip in. And
thank you, Warren. I think that is a good place to at least pause temporarily, because it's quite a dense things to So while everybody's preparing a question or thinking about something they want to ask, just to help my poor brain, Warren, what are some of the myths then, or the truths that people hold as, you know, this is what science says, we know this because science tells us this, that you think are not as true as people think they are, or you know, could you name some key some of those key ones maybe?
Well, obviously, if I go back in history, I've got what other people have said since and what further data they've accumulated on my side. If I'm trying to look at what's going on now, it's a little bit like crystal ball gazing. You know, we know that there's history should tell us that a lot of what we think is true now, we will think differently in 100 years' time. So, I mean, one of the things I think we may have discussed, there are assumptions in physics, for example, that because I think you've been reading Rupert Sheldrake, haven't you? He picks up on these. There are assumptions that the speed of light and the gravitational constant, etc., are universal constants, and they might be, but we've only been measuring them for, well, gravitational constant since Henry Cavendish a few hundred years ago, speed of light for about 120 years. Even within our measurements, we found subtle variations which don't seem to be explained very well. But it's a massive assumption that the speed of light in a distant part of our universe billions of years ago was the same. I've no idea whether it's true or not. So there are certainly things like that. I'm sure that some of the theories in evolution will be modified. So I'm sure there's going to be lots of theories getting modified.
We should thank Warren very much for such a wonderful presentation and giving everyone a jumping off point to think about this relationship between science and religion more deeply, with more nuance. I could hand over to you, Philomena, if you like.
Yes, thank you very much, Warren. That was great. That's exactly what we're about. It's about triggering thought, and I think we've just, you know, come up between us all, you know, just come up with some points which, you know, we could address, and that's great. Thank you very much, Warren, for such a clear presentation, and that's great. Thank you.